In this video, we're going to talk about the fundamental theorem of algebra, and we're going to see some verifications of it using factoring. So first of all, the fundamental theorem of algebra. Every polynomial of degree n greater than or equal to 1 has exactly n zeros. So in other words, the degree of the polynomial matches exactly how many zeros it has. Now that's including what we call multiplicity and complex zeros. So first of all, note, when we say multiplicity of a zero c, it's how many times x minus c occurs as a factor when you factor the polynomial. So let's first see some examples of the fundamental theorem of algebra, and then we'll go ahead and see how that helps us find zeros, or what it means when we go ahead and find zeros. So for example, the polynomial p of x equals 4x cubed plus 3x squared minus 5 has 3 zeros because the degree is 3. The polynomial h of x equals 17x to the 8th minus 2x to the 7th plus x to the 5th minus 4x cubed plus x has 8 zeros because the degree of the polynomial is 8. And the final polynomial 3x to the 5th minus 4x cubed plus 1 has 5 zeros. In other words, the degree of the polynomial tells you how many zeros you can expect. Alright, let's go ahead and find some zeros of polynomials now. So let's find all the zeros of p of x equals x to the 4th minus 2x cubed plus 10x squared minus 18x plus 9. So from the fundamental theorem of algebra, I know this polynomial has 4 zeros, including multiplicity. So let's find the zeros and then state their multiplicity. So in the road, or on the road to finding zeros, a good place to start is with the rational zeros theorem, which we've covered before. So the way the rational zeros theorem works, or principle if you will, is you take divisors of the constant, which would be 1, 3, and 9, and then you divide them by the divisors of the lead coefficient, which is 1. And that gives you possible rational zeros. In this case, 1 over 1, 3 over 1, and 9 over 1. So we're going to check positive and negative 1, positive and negative 3, positive and negative 9. So let's start with 1. So we're going to do that using synthetic division. So we do 1, just like before, and we write down the coefficients of the polynomial. So 1, negative 2, 10, negative 18, and 9. So remember, this is how we check to see if 1 is a zero of this polynomial. So it's going to be 1, multiply 1 and 1 and get 1, add negative 1, multiply negative 1, 9, 9, negative 9, negative 9, and 0. Okay, so because the remainder is 0, that means 1 is a 0. Now that means that this polynomial can be written as, in factored form, p of x can be written as x take away 1, because 1 is a 0, times the quotient, which would be given by this line here. So it'd be 1x cubed minus x squared. So x cubed minus x squared plus 9x minus 9. Now let's ask ourselves, is 1 also a 0 of this polynomial? So we're going to use synthetic division again, but on this. So here we go, it's going to be 1. And I'm just using 1 because it's the simplest number out of this collection. So I've got 1, negative 1, 9, and negative 9, where I'm using the coefficients of this polynomial. So bringing that down, 1, 1, 0, 0, 9, 9, and a remainder of 0. So again, 1 is a divisor, or sorry, x minus 1 is a factor of that polynomial. So now our polynomial can be written like this: x minus 1, but then this can be written as x minus 1 times the quotient here, which is x squared plus 9. So I've managed to factor this polynomial down to x minus 1 times x minus 1 times this. So we almost have all of our zeros, right? We have a 0 of 1 occurring twice, and now we have to find the zeros of this. And the way you do that is you set x squared plus 9 equal to 0, and you solve that. So using the quadratic formula, or in this case simply subtracting 9 from both sides, you get x is equal to positive or negative the square root of negative 9. So x is equal to positive or negative 3i. So we have our zeros. Let's list them, and let's write their multiplicity as well. Okay, so the first zero we found was 1. Now what's the multiplicity of that 0? The multiplicity is 2 because it occurred as a 0 twice, right? X minus 1, x minus 1. The multiplicity is as many times as that occurs, which in this case is 2. The other zeros are positive 3i and negative 3i because they are the numbers that cause this to be 0. So 3i is a 0 and negative 3i is a 0, and they occur only as zeros once, right? Because in other words, I don't see 3i twice. I only see it once because it occurs once as a 0 of this. So 3i is a 0. The multiplicity of 3i is 1. Negative 3i is a 0, and its multiplicity is 1. Okay, so how many zeros do we have? Well, if you include their multiplicity, we have a total of 4 zeros. 2 plus 1 plus 1. So that's how it goes when you look for zeros. You don't just count the number here, you include their multiplicity. And when you add the multiplicities together, that is what the fundamental theorem of algebra predicts, that the sum of the multiplicities will match the degree of the polynomial you started with. Okay? Let's see how we can also use the fundamental theorem of algebra in a different way. Find a polynomial p of degree 3 with integer coefficients and zeros of -2 and 1 plus I. Okay, so first of all, we're looking for a polynomial of degree 3 with integer coefficients, right? Now, integers are real numbers, and we know that when a polynomial has real numbers, so when a polynomial p has real coefficients, I should say, when p has real coefficients, remember it's complex zeros occur as conjugates. In other words, we're looking for a polynomial with real coefficients, and that means if 1 plus I is a 0, then so is its conjugate, which is 1 minus I. Okay, so we're going to have the zeros of, they gave us -2 and 1 plus I, but because the form of the polynomial we're looking for has real coefficients, integers are real numbers, I know that 1 minus I has to be a 0 as well. Now, whenever you know the zeros of a polynomial, you can construct a polynomial with those zeros, and the way you do that, of course, is by writing p of x is equal to, okay, x take away all the zeros, well, x take away the zeros, and all those factors multiplied together. So first, it's going to be x minus this 0. So it's going to be x minus -2. That's going to be one factor of our polynomial. X take away the second 0. X take away 1 plus I. And then, finally, x take away the third 0. X take away 1 minus I. So we have a theorem that says that when a number occurs as a 0, then x take away that value occurs as a factor of that polynomial. Okay, now we're going to multiply all these together to get our polynomial that is of degree 3 and has those zeros. Now notice that you're multiplying x take away this 0, 1 plus I, and also x take away its conjugate. Now, when you multiply those together, what's going to happen is you're going to end up, the product of these two is going to end up being a real quantity. So that's always the case. When you take x take away a complex number multiplied by x take away its conjugate, when you multiply those together, you're always going to get a polynomial with real coefficients. All right, let's see that happen here. So this is going to become x plus 2. Okay, and then I'm going to multiply these together. So x times x is going to be x squared. And then x times this is going to be, let's write, minus 1 minus I times x. And then when I multiply these together, I'm just basically foiling it out. So minus 1 plus I times x. And then finally, this number times that number, so it's going to be plus 1 plus I. Let's write that again. Plus 1 plus I times 1 minus I. Okay, and the plus, because it was positive because the negative and the negative was positive. So this ends up being x plus 2 times x squared. Let's go ahead and distribute the negative with the x. distribute it across this. So it's going to be negative x, and then plus ix, and then minus x, minus ix, because the negative x times 1 and negative x times positive I. And then finally, when you multiply these together, it's going to be plus 1 minus I plus I, and then minus I squared. So we're looking at x plus 2 times, let's see, we have some cancellation here, x squared. Okay, negative x and negative x leaves us with negative 2x. Positive ix and negative ix, those cancel, right? When you add them together, you get 0. And we have plus 1, and then negative I and positive I cancel. Now negative I squared is negative 1, and negative negative 1 is positive 1. So we end up getting this, x plus 2 times x squared minus 2x plus 2. And then finally, multiplying those together, you're going to get distributing x cubed minus 2x squared plus 2x, and then plus 2x squared again. Now I'm distributing this too. Minus 4x plus 4, and then our answer is going to be x cubed let's see, the negative 2x squared, I guess those cancel. Negative 2x squared and positive 2x squared. Positive 2x minus 2x is minus 2x, and then plus 4. So this is the polynomial. This is a polynomial that has negative 2, 1 plus I, and 1 minus I as zeros. And you can check that. How can you check this? And the answer is you can try to factor it. And when you factor it, you'll find that you get those zeros. Now notice that you could create other polynomials that have these as factors as well, that have these zeros as factors as well. And the way you do that is you'd put an arbitrary constant out here, a real number. If you multiply these factors by a real number, that won't change the zeros. And well, if you want integer coefficients, you want to make sure that it's a whole number or an integer. But in other words, there are infinite number of polynomials that have these zeros. Okay, so that's how you use that's how you use the fundamental theorem of algebra, and that's how you find zeros of polynomials. Until next time.